If you were buying a high-end sports car, and the dealer proudly informed you that it featured a quote-unquote fake V8 engine, you would probably laugh in their face.
Yeah, I mean, you'd immediately walk right off the lot.
Exactly. But in the ultra-precise, multi-million-dollar world of aerospace and industrial manufacturing, actively choosing to buy the fake version of a heavily hyped technology is, well, it's frequently the absolute smartest decision a company can make.
It is a completely counterintuitive reality.
Right.
And today, we're diving into a massive debate in the machining world, one that's centered around a highly controversial, heavily debated label.
And that label is fake five-axis machining.
Exactly.
We are going to unpack why that label even exists in an industry that is honestly obsessed with extreme precision. We'll look at the actual violent physics of cutting metal.
Yeah, and we'll figure out why settling for this so-called fake setup might actually be exactly what you need to do.
Okay, let's unpack this. In a sector driven by premium specifications, why on earth are engineers throwing the word fake around?
Well, what's fascinating here is that it all stems from a fundamental misunderstanding of machine architecture.
Really? Like a terminology issue?
Yeah, basically. The term fake five-axis is essentially slang, and fairly misleading slang at that.
Right.
The formal industry term is actually 3+2 positioning machining, or, sometimes you'll hear it referred to as indexed five-axis.
So where does the word fake even come from?
The fake label only really caught on because of a direct side-by-side comparison to the gold standard in the industry, which is premium, simultaneous five-axis machines.
Okay, I want to clarify how this 3+2 positioning actually operates under heavy cutting loads. Because assuming you're familiar with the standard X, Y, and Z linear axes, the ones that do the heavy lifting in any CNC mill, how did the rotary axis factor into this whole equation?
So the +2 refers to those rotary axes. Typically, that's a trunnion table that tilts, or maybe a swiveling spindle head that pivots.
Gotcha.
In a 3+2 setup, those rotary axes are designed strictly for positioning.
Meaning they don't move while cutting.
Right. They rotate the raw block of metal to a highly specific, mathematically programmed angle. And here is where it earns that fake moniker.
Okay.
Once it reaches that target angle, the rotary axes stop completely.
Yeah.
They trigger these heavy mechanical brakes and lock dead into place.
Wait, so during the actual cutting sequence, when the spindle is buried in the metal pulling heavy horsepower, those two rotary axes aren't moving at all.
Not even a fraction of a millimeter.
They're basically just dead weight.
They are entirely stationary, yeah.
Okay.
All the physical metal removal is handled exclusively by the simultaneous movement of the X, Y, and Z linear axes.
Oh, wow. Good.
And then once that specific surface is machined, the cutting tool retracts to a safe distance.
Mm-hmm.
The rotary axes unclamp, index apart to a brand new orientation, lock down again with those heavy brakes,
Yeah.
and then the linear cutting resumes.
Okay, so the contrast here is with simultaneous five-axis, where all five axes, linear and rotary, are constantly interpolating together while the tool is actually engaged in the metal.
Exactly. They're all moving at once.
Yeah. It's like painting on a canvas, I guess. The 3+2 method is like setting a canvas on an easel, tilting it to a flat angle, tightening the wing nuts so it's locked solid, and then painting.
That's a great way to think about it.
And to paint the side, you stop, unlock, rotate, relock, and then start painting again.
Right, right. And a true simultaneous five-axis operation would be like trying to paint that same canvas while it is actively twisting and tilting and rotating in midair.
With your brush dragging across it the entire time.
Exactly. Which requires incredible control.
And sounds absolutely exhausting to program. I mean, if I'm just painting a flat square, having the canvas do acrobatics is just showing off.
Yeah, it's overkill.
So practically speaking, what kind of geometries are actually the right fit for this locked-in 3+2 approach?
The determining factor is really tool orientation. If a feature can be completely machined from a single fixed tool direction, then 3+2 is absolutely the optimal choice.
What kind of parts are we talking about here?
We see this dominating the production of multi-sided components. Think gearbox housings, hydraulic valve blocks, cylinder heads.
Oh, okay. Complex aerospace brackets, too.
Absolutely, because you are dealing with flat planes, straight wall cavities, threaded holes, and standard pockets that are just distributed across multiple faces of a solid block of metal.
Right, so the machine just tilts the block, locks it, drills the holes, indexes again, mills the flat plane, and moves on. I see the utility there.
It's incredibly efficient for that specific work.
But let me challenge this premise for a second. Even if 3+2 works for blocky parts, it still feels like a compromise, like it's the budget option.
A lot of people think that.
Right. If I'm a top-tier manufacturer building critical components, why wouldn't I just buy the continuous 5-axis machine to handle everything? Isn't it just inherently more capable?
Well, that assumption makes perfect sense if you're just looking at a spec sheet, but it completely ignores one of the most critical foundational concepts in multi-sided manufacturing:
Which is?
qualm clamping.
Okay, let's explore that. What makes one clamping so vital to precision?
Consider the process of machining a complex hydraulic pump body, right? And it has critical features on 5 different sides.
Okay, 5 sides.
If you rely on a traditional 3-axis machine, you secure the raw stock in a vise and machine the top face.
Simple enough.
But to access the next side, an operator must physically stop the machine, open the vise, extract the part, blow off the metal chips, rotate it manually, seat it in a new fixture, clamp it down, and dial in its position all over again.
Manually.
Manually. And you repeat this intervention for all 5 sides.
That sounds incredibly labor-intensive, and I have to imagine you're opening the door for human error every single time that vise opens.
Oh, absolutely. You're introducing stacked tolerances.
Stacked tolerances.
Yeah, because every single time a part is refixtured, microscopic alignment errors occur.
Oh, I see.
Think about it. A human hand cleaning a vise might leave a single 0.001-inch chip of aluminum behind.
Just one tiny chip.
Right. And when you clamp the part on top of that chip, the part is now skewed. You also introduce variations in clamping torque or tiny thermal expansion discrepancies.
And those just build up over time.
Exactly. Over 5 setups, those microscopic deviations compound. So by the time you machine the final side, a critical dowel pinhole might be entirely out of concentricity with a bearing bore on the completely opposite face.
Which means the part fails inspection and goes straight into the scrap bin.
Yep, total loss.
So 3+2 solves this by keeping the part bolted in the machine, one clamping, and the rotary table just exposes the different sides to the spindle.
Exactly. The original reference point is perfectly preserved. It entirely eliminates the human variable in the setup.
Huge.
But the advantages of 3+2 actually go much deeper than just positional accuracy. And that brings us to a fascinating engineering reality that we can call the rigidity paradox.
Okay, the rigidity paradox. Because I am honestly struggling with the physics here.
How so?
Well, a true 5-axis machine is the premium top-tier technology. Shouldn't a $1 million continuous machine be far more rigid and stable when it's hogging out heavy titanium than a machine that just, locks into place?
You would assume so, naturally. But a 3+2 process frequently delivers vastly superior dynamic cutting stability.
Really? Superior stability.
Yeah. To understand why, we have to look at the mechanisms that actually hold the axes in place under the extreme violent forces of metal cutting.
Okay, let's break that down.
In 3+2 machining, once the rotary axes reach their position, heavy mechanical brakes engage.
Right, you mentioned the brakes.
You have a physical, friction-based mechanical deadbolt immobilizing that trunnion table.
So it essentially becomes a solid monolithic block of cast iron at that point.
Yes, exactly. Contrast that with a true simultaneous 5-axis machine.
Okay.
Because the rotary axes must remain capable of instant movement during the cut, they cannot utilize mechanical brakes.
Oh, right. They have to keep moving.
Exactly. They rely entirely on servo motors, holding their position electronically while in motion.
So the motors are just fighting the cutting force.
Yes, the machine's control system is constantly battling the aggressive forces of the cutting tool.
Let me see if I can visualize this difference in force. It sounds like the difference between trying to hold a wildly bucking, high-pressure fire hose steady, using only your arm muscles, which would be the servo motors constantly flexing and adjusting,
Right.
versus taking that same fire hose and just strapping it directly to a massive concrete pillar, which is the mechanical brake.
That is a phenomenal analogy. The servo motors are incredibly strong, sure, but they are reactive.
What do you mean by reactive?
When the spinning cutting tool slams into a hard spot in the metal, it generates a massive force spike. Servo motor senses that deviation, and the control system commands more electrical current to push back.
But there's a delay.
Exactly. There is a microsecond of lag in that communication loop.
And in machining, a microsecond of lag translates to physical vibration.
Yeah, we call it chatter. The control system is constantly hunting for position, dealing with rotary backlash, and reversing loads.
And I imagine chatter is bad news.
Oh, it destroys surface finishes and shatters incredibly expensive carbide cutting tools. The mechanical deadbolt of a 3+2 system simply does not have that vulnerability.
Wow, that is a massive revelation. You're fighting the vibration with a concrete pillar instead of active electronics.
Exactly.
And there is another layer to this rigidity involving the tooling itself, isn't there? Something regarding tool overhang.
Yes. Tool overhang is the silent killer of cutting stability.
Okay, so imagine you need to machine a deep cavity, right? And the workpiece is sitting flat on a standard table.
Right.
To reach the bottom of that cavity without the massive spindle housing crashing into the top of the part, you're forced to use an exceptionally long cutting tool, like an extended reach end mill.
And mathematically speaking, a cutting tool is just a cantilevered beam.
Right, it's a lever. If you press a 12-inch steel rod against a wall, it flexes and bends. But if you press a 2-inch steel rod against the same wall, it barely deflects at all. So in a machine, that flexing lever amplifies the chatter we just talked about.
Yes, it compounds the problem. But by tilting the entire workpiece in a 3+2 setup, you can actually angle that deep cavity so it points directly at the spindle.
Oh, I see.
This completely clears the housing obstruction and allows you to swap out that 12-inch tool for a rigid, stubby 2-inch tool.
Swapping a flexing lever for a rigid spike.
Precisely.
So by using the quote-unquote less advanced cutting mode, you can actually push the machine much harder. You can increase the feed rates, take heavier depths of cut, and remove metal much faster.
And the economic impact of that is staggering. Faster material removal means cheaper parts and significantly higher profit margins.
That makes total sense. I mean, if 3+2 gives us concrete pillar rigidity and lets us use stubby, aggressive tools, it sounds invincible.
It does sound that way, doesn't it?
But here's where it gets really interesting, because there has to be a hard boundary line where 3+2 simply fails, right?
Oh, it absolutely hits a wall. And it brings us right back to our twisted canvas analogy from earlier.
Okay.
The definitive kryptonite of 3+2 machining is a continuously changing free-form surface.
What does that actually look like on a manufacturing floor?
The classic example is a blisk.
A bliss.
Yeah, a bladed disc used in jet engine compressors. Or think of a turbocharger impeller, a marine propeller, or highly complex aerodynamic mold.
Stuff with crazy curves.
Right. These surfaces do not have flat planes. The geometry curves and twists in 3 dimensions simultaneously.
Meaning the optimal angle of the cutting tool relative to the metal changes at literally every micromillimeter of the tool path.
Exactly. So if you lock the axis, the tool will instantly gouge the material as the curve falls away or rises up.
But wait, software is incredibly powerful now. Couldn't you take that sweeping, twisted impeller blade and instruct the CAM software to break it down into thousands of tiny, flat 3+2 steps?
Like a staircase?
Yeah. Cut a millimeter, lock, index half a degree, lock, cut another millimeter.
Well, you could generate that code. The math completely allows it.
But
the physical reality would be a total failure. For one, the cycle time would be astronomical due to the constant clamping and unclamping of those rotary brakes.
all that stopping and starting.
Yeah, but the fatal flaw is actually the surface finish.
Because of the transitions between those tiny steps?
Yes. Every time a cutting tool stops, lifts, and re-engages at a slightly different angle, it leaves what we call a witness mark.
Witness mark, like a tiny ridge.
Exactly. A microscopic step or a junction line where those two planes meet.
So instead of a perfectly smooth, sweeping aerodynamic surface, your highly engineered jet engine blade looks and feels like it was built out of tiny pixelated Legos.
Right. And in fluid dynamics, those microscopic steps cause turbulence, inefficiency, and even stress fractures.
That sounds dangerous for a jet engine.
It is. Parts designed to manipulate air or water demand the smooth, continuous sweeping motion of true simultaneous 5-axis interpolation to maintain unbroken surface contact.
The tool never lifts, so there are no junction marks.
Exactly.
But there's also a physical space problem, isn't there? When I picture a tool trying to navigate deep between two tightly spaced, curved turbine blades, it seems like a locked axis would be incredibly dangerous.
You have hit on a massive limitation of 3+2, collision avoidance.
How does simultaneous handle it differently?
A simultaneous 5-axis machine acts almost like a dancer. As the tool drives deep between two blades, the software is elegantly tilting the spindle mid-cut.
Constantly adjusting the tool vector.
Right, to actively dodge the neighboring blade or the work-holding fixture.
Just ducking and weaving while cutting.
Yes. But a 3+2 machine is blind and locked once the cycle starts. It cannot dynamically dodge an obstruction.
Oh, wow.
If the fixed angle isn't absolutely flawless, the body of the spindle will plow directly into an adjacent blade, or worse, crash into the cast iron rotary table itself.
And a spindle crash is not just a small fender bender. We are talking about a violent, ear-shattering impact that can cause tens of thousands of dollars in damage in a fraction of a second.
Absolutely. It destroys the spindle bearings and completely ruins the machine's geometry.
So the division of labor is really clear. 3+2 dominates blocky, multi-sided parts with its locked rigidity, and continuous 5-axis is mandatory for swoopy aerodynamic parts.
Precisely.
But let's say I'm a shop owner analyzing my production. I realize 90% of my parts are valve blocks and gearboxes. I want that 3+2 efficiency, but I don't want to spend $500,000 on a brand new machine.
I see where you're going with this.
Can't I just buy an aftermarket trunnion table, bolt it to the bed of my old 3-axis machine, and basically create a Frankenstein 3+2 mill?
Well, the aftermarket conversion route is extremely common, actually, but it is incredibly risky.
Why is it risky?
You can physically bolt a 2-axis tilt rotary table onto a standard 3-axis vertical machining center, but treating it as a simple hardware plug-and-play is a massive miscalculation.
Let's look at the physical reality first. You are taking a massive chunk of iron and just dropping it into an enclosed workspace that was never designed for it.
Right. You are fundamentally altering the machine's spatial envelope.
How so?
A standard 3-axis machine has a very specific Z-axis clearance that's the distance from the spindle nose down to the table. When you bolt a tall trunnion unit onto that table, you elevate the mounting surface significantly.
You have effectively raised the floor of the machine.
Yes.
So a tall workpiece that used to fit perfectly might now sit so high that the spindle can't physically retract far enough to clear it.
Exactly. You hit the Z-axis limit switch before you even finish the part.
Mm-hmm.
Furthermore, you have to consider the structural integrity.
The actual frame of the machine.
Yeah. The linear guideways and ball screws on that older 3-axis machine were engineered to handle vertical loads from a flat table. When you tilt the heavy part 90 degrees and start aggressive side milling, you're introducing massive torsional force vectors that the machine frame was never designed to absorb.
Mechanically, you risk tearing up the guideways or inducing intense vibration.
Yes.
But the underlying technical data suggests the hardware is actually the easy part. The real nightmare is the software integration, right? You have to give this old machine a brain transplant so it understands it suddenly has 2 new limbs.
Exactly. The CNC controller only knows the parameters it was originally programmed with.
Makes sense.
Adding 2 rotary axes requires new servo amplifiers, axis control cards, and really complex parameter tuning. But the most critical software hurdle is a mathematical function called RTCP.
Rotation tool center point. Let's break down the math on this because it seems to be the linchpin of modern multi-axis machining.
It is. Imagine your cutting tool is hovering exactly 1 inch above a specific hole on your workpiece.
Okay, hovering 1 inch above.
If you command the aftermarket rotary table to tilt 45 degrees, what happens physically to that hole?
Well, since the table pivots around a central fulcrum, that hole swings along a physical arc. It moves down and away from the tool.
Right. The spatial coordinate has completely relocated. If your machine's brain lacks RTCP, it has no idea that hole moved.
It still thinks it's in the same spot.
Yes. It still thinks the coordinate system is perfectly aligned with the original flat position.
It is entirely blind to the rotation.
RTCP is the internal mathematical capability of the controller to continuously track the exact pivot point of those rotary axes in 3D space.
Ah, I see.
It calculates the arc and dynamically shifts the entire coordinate system so the tool still knows exactly where that hole is, regardless of the tilt angle.
Wow. So if your older 3-axis machine doesn't have RTCP or similar kinematic transformations like G68 or CYCLE 800, how do you even program it? Like, how do kinematic transformations actually work without it?
Well, a kinematic transformation is a software command that essentially tells the machine's brain, hey, the entire universe just tilted 45 degrees. The Z-axis is no longer straight up and down relative to the floor. Z is now perpendicular to this new tilted plane.
Okay.
Without that capability, it becomes a brutal exercise in manual trigonometry.
That sounds horrible.
It is. The programmer has to calculate the exact center of rotation of the physical table, factor in the exact length of the tool, and manually offset every single line of G-code.
And if the CAM software and the post processor are off by even a fraction of a millimeter, regarding where that physical pivot point actually is?
The computer commands a plunge, but the metal isn't where it expects it to be.
Oh,
The
no.
tool plunges into the steel fixture, or the table rotates directly into the spindle housing.
Another catastrophic crash.
Exactly. Which is why a purpose-built 3+2 machine engineered from the ground up where the kinematics, the RTCP mathematics, and the physical iron are perfectly synchronized by the manufacturer is invariably the safer, more productive route.
So what does this all mean? We open this deep dive looking at a term that sounds like a massive insult, fake five-axis. But the evidence clearly vindicates this technology. The fake label is nothing more than industry snobbery. Axis count is not a metric of quality.
Not at all.
3+2 positioning is a highly deliberate, incredibly rigid solution that uses mechanical deadbolts to conquer stacked tolerances in multi-sided parts. Meanwhile, simultaneous 5-axis remains the undisputed king of complex, twisting aerodynamics where the tool really needs to dance.
It serves as a powerful reminder for anyone evaluating technology, do not fall victim to spec sheet marketing.
Yeah, more axes isn't always better.
Right. It is always about marrying the correct mechanical architecture to the specific geometry of the task. Deploying continuous 5-axis for a hydraulic valve block is a staggering waste of capital and rigidity.
Just as retrofitting a 3-axis mill to cut a turbine blade is an open invitation to disaster.
Absolutely.
Well, I want to leave you with a final provocative thought to mull over as you go about your day. We spent a lot of time today exploring how 3+2 achieves its legendary stability through heavy physical iron mechanical brakes and solid locks.
Right.
But computing power isn't standing still. As AI-driven servo motors evolve, becoming capable of predicting and counteracting physical cutting vibrations in microsecond intervals, will the physical rigidity of 3+2 eventually be entirely replaced?
It is definitely the next great frontier in machining kinematics.
Are we witnessing a transition from an era where stability is generated by heavy iron and mechanical deadbolts to an era where stability is synthesized by heavy code and digital dynamic stiffness?
It's a huge possibility.
Will simultaneous machines eventually become so intelligent that they perfectly mimic the rigidity of a locked cast iron table? It's something to think about the next time you turn a key or board a flight and wonder how those flawless metal parts were actually born. Keep questioning the labels on the technology around you. We'll catch you next time.